Here we have two 100 ohm resistors that are connected in parallel, and then we'll do part B, which will be in series, and it's connected to a 24 volt battery. What is the current through each resistor, and what is the equivalent resistance of each circuit? The first step is to start with Ohm's law. We can rearrange this equation to solve for current. First we'll do I1, and we know the value for R1, and we also know the voltage across R1 because the resistors are in parallel. The voltage across R1 of 100 ohms is 24 volts, and we can calculate the current to be 0.24 amps. Now, since R1 and R2 have the same resistance, the current flow through R2 is also 0.24 amps, and that's only because they're the same value of resistance. Now, to calculate the equivalent resistance, we need to use the equation for resistors in parallel. Plug and chug to get 1 over 50, but this is not the answer yet. We need to take the reciprocal to calculate the equivalent resistance of 50 ohms. Now, if we want to calculate the total current, just add up I1 and I2, which are the same value, and we get 0.48 amps. Now, for the resistors in series, let's calculate the equivalent resistance first by using this equation for resistors in series. Plug and chug to get equivalent resistance of 200 ohms. Now, to figure out the current through the resistors, we can use Ohm's law. Rearrange the equation to solve for current. Plug and chug, and the voltage and the equivalent resistance to get 0.12 amps. Now remember, the current through the resistors in series is the same value for both R1 and R2. Next example, how much current is drawn from the battery? The first step in calculating the equivalent resistance is to combine the two resistors in parallel. Plug and chug with the equivalent resistance equation for parallel to get 290 ohms. And now we can calculate the total equivalent resistance of the circuit by using the equation for resistors in series to get 690 ohms as the equivalent resistance of the whole circuit. And then from there, we can use Ohm's law to calculate the current drawn out of the battery, and we get 0.0174 amps. In this example, we want to figure out what is the current I1 through the 500 ohm resistor. To attack this problem, you would need to first solve for the equivalent resistance of the whole circuit and calculate the current. Now, we already did both of these calculations in the previous example. We know the current through the 209 ohm resistor is 0.0174 amps. And we know 290 ohms was calculated from parallel resistors. And we know that parallel resistors have the same voltage. What we don't know is the voltage across the 290 ohms. So to calculate the potential difference between point B and C, we can just use Ohm's law. Plug and chug and we get 5 volts. Now we can calculate the current I1 through using Ohm's law because we know the voltage across 500 ohms to be VBC. Plug and chug and we get 0.01 amps or 10 milliamps. Now the circuit has 3 identical light bulbs, each resistance R. For part A, when the switch S is closed, how will the brightness of the bulbs A and B compare with that of bulb C? Well, the amount of current drawn out of the battery, or the voltage source, depends on the total equivalent resistance. The current will travel from the battery through light bulb C and then split at the node, like a river splitting at the fork in its path. The current will travel through light bulb A and B will be less than C because the total current going through C is split between A and B. Now, since A and B are identical light bulbs, the current will be the same through A and B, and their brightness will be the same, but less than C. And then for part B, what happens when the switch S is open? If S is open, then the light bulbs C and B are now in series and will have the same amount of current. Also, since the total equivalent resistance is different, the amount of current drawn from the battery will be different. In fact, the current will be less because of the higher equivalent resistance. In this example, we have a 9-volt battery whose internal resistance, little r, is 0.5 ohms and is connected in a circuit. For part A, how much current is drawn from the battery? And then for part B, what is the terminal voltage of the battery? And then part C, what is the current in the 6 ohm resistor? So for part A, the first step is to calculate the total equivalent resistance. To do so, we'll combine the first two resistors in parallel. With the parallel equation, we get 2.7 ohms. Now the circuit is reduced, and from there we can calculate the combined two resistors in series to get 8.7 ohms. Now the circuit is reduced even further, and we can combine the two resistors that are now in parallel with each other. And we get 4.8 ohms. From here, we can combine all the resistors together, even the internal resistance, little r, to get the total equivalent resistance of 10.3 ohms. Knowing the total equivalent resistance of the whole circuit, we can calculate the current drawn from the battery with Ohm's law. Ohm's law can still be used with EMF. Plug and chug, and we get 0.87 amps drawn from the battery. Now for part B, the terminal voltage that is defined at point A and B can be found with an equation that we used earlier in this chapter. Plug and chug to get a terminal voltage of 8.6 volts, which is not surprisingly less than 9 volts. Now, to calculate the current through the 6 ohm resistor for part C, we already know the current drawn out of the battery, so we can use that to figure out the voltage between A and C, because we know that the 4.8 ohm was calculated from two resistors in parallel, and the voltage stays the same across resistors in parallel. So plug and chug to get voltage for BC to equal 4.2 volts. Excuse me, AB. Now we can split the 4.8 ohms back into two parallel resistors. And the voltage between A and C is the same across resistor 8.7 ohms. Now 8.7 ohms was calculated from two resistors in series. And we know the current is the same through resistors in series. And we can calculate this current, I2, with Ohm's law. Plug and chug to get 0.48 amps. Now let's split the 8.7 ohms back into two resistors in series. And we see the current is the same through both resistors. And we just answered the question, what is the current through 6 ohm resistor, which is 0.48 amps. Now, in this course, we will not use Kirchhoff's rules in a circuit that is in this kind of circuit that's more complicated. The last example that we just did, that will be the hardest type of circuit that you'll see. But what I want to do is I want to go over the basic rules for Kirchhoff's. One is called junction rule. The sum of the current entering a junction equals the sum of the current leaving it. So I1 plus I2 equals I3 according to this circuit diagram. And again, think of a river. If branch 1 and 2 combine, you will have more water. In fact, add 1 and 2 together to get the combined total flow. Points A and D are considered the nodes, because when I3 runs into point A, it will split its current. Part of it flowing down I1, and then the rest will flow down I2. Now, the second Kirchhoff rule is a loop rule. The sum of the charges the sum of the change in potential around a closed loop is 0. We know that E is the highest potential and D is the lowest potential, or potential of 0. So if we start at point D, we start at 0 potential. When we go through the battery and now have the highest potential at point E. Now going to point A, we cross no resistors, so the potential remains the same value. Point B, the potential drops, and the potential difference between points A and B is 7 volts. Moving to point C, the potential drops again, but this time all the way to 0 because that's the end of the resistors before coming to the battery. So points C and D have the same 0 potential value because there's no resistor. And the potential difference between points B and C is 5 volts. So if we calculated 12 volts to start with and then subtract 7 and 5 volts, we would get 0 volts. And that is the Kirchhoff's loop rule.